Okay, I'm going to try to derive the proof for one of these for you, so you can see where they come from. These are going to be two formulas that, or not two, a few more formulas that you're going to need to know and learn. So as you build your formula sheet of things that you guys need to be able to do, this is a big one. Okay, one of the ways we derive mathematical formulas is we come up with two different ways to express the same thing, set them equal to each other, and derive some conclusion about it. So this is one instance of where we're going to do that. We're going to presume that what we have here is a unit circle, which means a radius of 1. I'll just kind of throw that in the corner, but you don't necessarily have to write that because we don't want to crowd the figure. And I'm going to put two angles. First angle we'll just call alpha. And I'm going to put the angle right here and let this be representative of alpha. Maybe make it a different color so I know that that is angle alpha. It doesn't necessarily need to be a quadrant 2 angle, but I just drew it to give me some space. And the intersection of the ray from angle alpha and the unit circle would have coordinates, not just coordinates of x, y, but what would the coordinates be if that was a circle of radius 1? What would the x value be? Wouldn't be the yawn, but guess, Miguel. Even better, you didn't even have to say negative. If alpha is positioned wherever it is, it will take care of itself, positive or negative. So we're just going to say the cosine of alpha, which means, of course, that the y value is the sine of alpha. Some of they're incredibly awake right now. Okay, next, we're going to draw a second ray, and we're going to do this from the central point as well. But this one is going to be angle. No, I didn't want that to be orange. I want this to be orange. We're going to draw an angle. We're going to call that angle beta. That means B in Greekland. And the intersection of that ordered pair, oh, I should make these coordinates red. Trying to keep some consistency here. The intersection of that ordered pair with the unit circle would have coordinates of cosine beta, sine beta. So all I have are two angles, just kind of arbitrary ones, one in quadrant. Well, it doesn't even matter what in quadrant they're in. What I want to do is I want to connect the dots and find the distance between these two ordered pairs. That's going to be part of what my formula here is going to do. So I'm going to call that D1. Distance 1 is equal to, do you remember how to find the distance between two ordered pairs? Distance squared is equal to delta x squared plus delta y squared. Oddly enough, it's like you've seen that before, like 1,000 times, that relationship. But distance is equal to, this would be a big square root of the change of x squared, so cosine alpha minus cosine beta squared, plus, then you have a difference in the y's, sine alpha minus sine beta squared. That is distance 1. Cool, means nothing right now. What I'm going to do is this is the kind of the key part here, I'm going to actually try to express exactly the same thing. But, and I can show this with my hands, I'm not sure I can show this elsewise, I want to take this V here and I want to rotate it so that this angle, or this ray, beta ray, sits on the x-axis. I'm going to turn the whole thing to the right. And by doing that, I'm going to try to create the same angle. So what was ray B is now just sitting on the x-axis, like this. And what was ray alpha is now sitting kind of like that. And this angle here is now not angle alpha or beta, it's the angle between them, which we could actually express in terms of alpha and beta. What angle would that be? It would be alpha minus beta. And that means we can actually now label coordinates here and here in terms of that. Let's start with the top one. This is still a unit circle. this would be the cosine of alpha minus beta, comma, the sine of alpha minus beta. What would the one down at the bottom be? What would the coordinates here be? Don't overthink it. It's a unit circle, and it's on the x-axis. What would the x value be? 1. And the y value would be 0. The angle is 0, but this is just the ordered pair 1, 0. And if I connect the dots to these 2 points, and let's call that distance d2, that should be equal to the square root of the change in x squared, which would be cosine of alpha minus beta minus 1 squared, plus the sine of alpha minus beta minus 0 squared. What do you think I'm going to do with d1 and d2? Yep, say it loud, Carlos. I don't think the mic picked you up there, but we are going to set them equal to each other, yes. d1 should be equal to d2. They are basically the same 2 distances expressed differently. So now we just begin the algebra of this, which is sort of the burdensome part. I'm going to start by doing something simple. If d1 is equal to d2 and they're both big radicals, can't we just square both sides and drop the radicals? This is not proving an identity. This is deriving a formula. So my big one is going to be cosine of alpha minus cosine of beta squared plus sine alpha minus sine beta squared equals, parentheses, cosine of alpha minus beta minus 1 squared plus, and I think it's okay to write the sine of alpha minus beta squared without the minus 0. You know, minus 0 is kind of not needed now. So this is it. And if you're going to laugh at me now at the work we're going to have to do, and we're going to do this in a second. We are going to multiply everything out. Just be ready for that. It's going to happen here in about 4.5 seconds. Picture me doing this with my seniors last year, the senior pre-calc class. Picture that happening right around March or April, and trying to keep them attentive while we did the algebra of multiplying this out. That was fun. And also futile. Okay. As you might imagine, cosines plus sine squareds are going to happen all over the place here. So we're going to get a lot of stuff dropping out. Let's just kind of write it out once and then start crossing some stuff. So cosine squared theta minus 2 cosine alpha cosine beta plus cosine squared beta plus sine squared alpha minus 2 sine alpha sine beta plus sine squared beta equals, and I'm going to put this on another line, shifted because I have a horizontal space. So it equals cosine squared of alpha minus beta minus 2 cosine of alpha minus beta plus 1 plus sine squared of alpha minus beta. Which is kind of a lot, but it's not. It's definitely doable. How is it doable? Well, for one, I know that cosine squared plus sine squared, so this and this give me a 1. This and this give me another 1. That's 2 on the left. This and this give me a 1. That's 2 on the right, so that's 1 plus the 1 that's there. So I have 2 on the left and I have 2 on the right, which means, guess what happens to the 2's? Bye-bye. They're gone. No, all this crosses out because that, this, and that 1 cancel each other out, left and right sides. Then you actually have a situation where you have coefficients that are all -2, which means those can go away. We can factor a -2 out of both sides and divide those out. And if I flip things around a little bit, I end up with the cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta, which is actually the point of what we were trying to arrive at. This is a difference formula. The cosine of the difference of two angles gets that. And that's not a formula. This is even more important than a formula. This is an identity. And this is the first of 4 that you're going to have to know. I'm going to show you how it works. If you think about the actual, I'm going to show this on the grid too. If you think about the ones that you guys have been able to determine, and by the ones I mean the angles you've been able to determine, the ones you've been able to know from the grid have been, I'm just going to sketch this out, you don't have to draw this out, just kind of watch. We've been able to do right, up, left, and down. You've been able to do the 45-degree angles of all of them. And you've been able to do 30 and 60 and so forth. If you sketched all those out, you're actually somewhat missing a piece that would make them all perfect to each other. And I'll explain this. If you go 0, 30, 45, 60, and 90, what are you kind of missing in there to make them a kind of a perfect linear progression? Yeah, you're missing the 15 and the 75, which would make everything be 15s. Those are the pi over 12s, by the way. Every 15 degrees is a pi over 12. Why? I don't know. It should be a tau over 24, but that's a separate issue. So we get to this where I need to figure out what 15s and 75s are. If for no reason, then I'm just compulsive and I want to know what they are. And I am compulsive sometimes. Come on, some of you can relate. I know. Number 1, cosine of 15 degrees. This is one you guys can now do an exact value of. Here's how it's going to work. Jockey with me? 15 can be expressed as 45 minus 30. Do not tell me that that is equal to the cosine of 45 degrees minus the cosine of 30 degrees. That's not a thing. Okay? There is no distributive property of cosine across addition and subtraction. That is a variation of your favorite mean. My favorite mean. Don't kill puppies. There is no operation across addition and subtraction other than multiplication division. Just like the infinity between 1 and 2 is the same as the infinity between 1 and 3. We're letting the line stay because it's the line in the book, and you have to on. What? Yes, it's iconic because it creates discussion about how wrong it is. We're coming Wednesday, by the way. Yes. I haven't missed a rebuff production in a very long time. Not about to start now. Okay. Next, let's actually express this how it is. This is the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees, sine of 30 degrees. Hey, you know what all those are. You know that cosine of 45 degrees should be rapid like that. And I'm going to give you some advice. Express it as root 2 over 2 and not 1 over root 2. Because you're going to have a lot of over 2's happening here. It will be easier. Cosine of 30, there's 30. Root 3, 1, 2. Cosine of 30 is root 3 over 2. See, that's why we're doing them both over 2. Plus, isn't the sine of 45 the same as the cosine of 45? Root 2 over 2. And the sine of 30 is the one that's left over. 1/2. Simplify. This is going to be root 6 plus root 2 all over quattro. You now know the cosine of 15 degrees. Congratulations. Yep. Yes, Nate?
This is equal to cosine of 45 minus 30.
Oh, that's not equal. This is out.
Yeah, I know that.
But that's, yes, that's equal to cosine 45 minus 30. So we took 15, we expressed it as 45 minus 30, two angles we know, and then maneuvered it. Okay, little break line. Let's do the sum one. So I just said, or we just said, that the cosine of alpha minus beta is the cosine of alpha cosine of beta minus the sine of alpha times the sine of beta. Well, what if I did the cosine of alpha minus a negative beta? And I took the negative beta and I plugged it in so that this would be the cosine of alpha cosine of negative beta minus the sine of alpha sine of negative beta. Yes, Nate?
Isn't it plus sine of alpha?
Oh, it is plus. Thank you. That's plus. That's plus. Good catch already. You get what I'm doing here? I'm trying to derive the cosine alpha plus beta by just substituting negative beta in. We're going to use the even-odd identities to get this. What is the cosine of negative beta? Cosine of beta. So this is cosine alpha, cosine beta. What is the sine of negative beta? Negative sine beta. That negative is going to factor out and become minus sine alpha, sine beta. And this is cosine of alpha plus beta. And that's the second one. Now, you know me by now. You know I tend to like the plus minus minus plus notation. So can't we kind of simplify this whole thing just a little bit and write it as the cosine of alpha plus or minus beta equals the cosine of alpha cosine of beta minus plus the sine of alpha sine of beta. So this is the real one, knowing how the cosine, cosine, sine, sine works, and knowing that it's opposite sign. Speaking of sine, time permitting, I'm not going to prove this one right now. We have too many other problems to get to, but it's not too hard to derive this one using the co-function identities, the pi over 2 minus. The fact that, yikes, I want to get that bigger. Let's do the sine ones. Sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. And the sine of alpha plus beta is the sine of alpha cosine beta plus cosine alpha sine beta. Two more for you that I'll summarize the same way we did right up above. Sine of alpha plus or minus beta is sine alpha cosine beta plus minus cosine alpha sine beta. You'll use these a lot. It's not going to be too difficult to memorize them. I know it seems like it is right now, but I promise you it's not. There are plenty of ways to do several of the problems we're going to get to. So let's just kind of do a couple more examples of two that you're going to see. Sine of 75. So for instance, 75 is also one of the 15-degree ones, and to do that you need to take a 45-degree one and add or subtract it. You could express this as the sine of, what am I trying to say? This could be the sine of 75 plus 45. Why am I blanking on this? 120 minus 45. You could express this as the sine of 45 plus 30. You could express this as the cosine of 90 minus 75. Do you see all the different ways that you can do this? That last one's the cofunction identity. The sine of an angle is the cosine of the complement. So I'm going to practice with this one because that's the newbie here. That's, I think, the easiest, and I find it easy to deal with pluses and minuses, but it's just my world. So the sine of 45 degrees plus 30 degrees is equal to sine 45 cosine 30 plus cosine 45 sine 30. Sine of 45 is root 2 over 2. Even if you mess up which one's the cosine of 30 and which one's the sine of 30, it's not going to matter here because it's plus. It would just be either order. And you know the cosine of 45 is the same regardless. We won't mess that up because we're not those kind of people. But root 3 over 2 plus root 2 over 2 times a half. And oh, lo and behold, you get the same root 6 plus root 2 over 4. It feels like we're going to be seeing that one a lot. Okay, we're going to do another one. Cosine of 47 pi over 12. Why? Just because. Let's coterminal that. Let's kind of wrap that around and get it back to something reasonable. Like maybe subtract 24 a couple of times. I would argue that I think it's easier to even go twice. Subtract 24 twice from 47 and make it negative pi over 12, so you don't really have to think about it. But you can do it many, many other ways. So when you're dealing with 12ths, you got a couple options. That is negative 15 degrees, by the way. And if you have to convert it back to degrees to get your sums and differences going, I understand, because we're dealing with fractions. What I'm going to kind of do is just sort of play it out and say, well, I know that 3 and 12/12 will simplify to stuff that I know. So negative 1 is 2 minus 3. That's one way to get it. It's 2 minus 3. So I'm going to make that 2 pi over 12 minus 3 pi over 12. You could have also done 3 minus 4, and it would have been fine as well. But are these all, am I keeping equivalents in every single line here? Tracking this down, this becomes the cosine of pi over 6 minus pi over 4. And then we just make sure we use our cosine identity. Cosine pi over 6, cosine pi over 4. The cosine difference one is an opposite sign, so that's going to be plus sine of pi over 6, sine of pi over 4. Cosine, cosine, sine, sine. Cosine of pi over 6, let's draw it out, is that one. Root 3 over 2. Root 2 over 2 plus 1/2 root 2 over 2. And oh, okay, huge surprise here. We get root 6 plus root 2 over 4. All the 15-degree variants of sine and cosine are one of these four. Root 2 plus root 6 over 4, root 2 minus root 6 over 4, root 6 minus root 2 over 4, or negative root 2 minus root 6 over 4. Those are the only four possibilities for sine and cosine of the 15, 75, and appearing in all four quadrants. You don't need to know that. I mean, you will derive that every time you do it, and you need to show your work on that. It's only later that you can actually kind of skip ahead to one of these four, just by logic. If you know it must be one of these four, you can kind of actually predict which of the four it's going to be based on what you're trying to find. So, having fun with some difference, let's do one more set. Let's do the tangent of alpha plus beta. You knew that was coming. How do you think I'm going to derive tangent of these? What's the logical way to derive tangent? Absolutely. We're just going to do the sine over the cosine and try to get it in terms of tangent. Sine of alpha plus, or tangent of alpha plus beta is the sine of alpha plus beta over the cosine of alpha plus beta. Which is the sine of alpha cosine of beta plus the cosine of alpha sine of beta over cosine alpha cosine beta minus sine alpha sine beta. Now, to really be a good identity, you need to have it all be in terms of tangent. And the only way to do that, and this is going to be a little clever step, this sine alpha could be tangent if it was multiplied by 1 over the cosine of alpha. Then it would be a tangent of alpha. This cosine of beta can never be a tangent, so I need to clear it. I'm going to multiply it by cosine beta. And let's do that in the denominator too, and let's just see what happens when I multiply by 1 over cosine alpha cosine beta in the numerator and the denominator. The numerator becomes tangent of alpha plus tangent of beta. The denominator becomes 1 minus tangent alpha tangent beta. And that is a sum difference identity. I could use the negative properties and just kind of do the same thing we did before. If I substituted a negative beta in, then this would be negative and this would be negative, and it would carry the negative out because tangent's an odd function. So we would get the fact that tangent of alpha minus beta is equal to tangent of alpha minus tangent beta over 1 plus tangent alpha tangent beta. I don't memorize the tangent ones. I rederive them. It's just easier on me to go that far. You can memorize them if you want to, but you do need to memorize the sine and the cosine ones. So I'm going to wrap this up with an example of tangent and then just kind of leave it to you. The tangent of 285 degrees. I think it's easier to do a sum, and I think it's easy to subtract 45. And we get to here. So now it's just a matter of making sure you get the trig right, which is going to be crucially important that you have your trig completely mastered to get these. Tangent of 45 is the tangent of that angle, which we know to be 1. 240 is, gosh, in a way it's almost easier when it was radians now. 240 is where? It's angle quadrant 3. 60-degree angle in quadrant 3. 60 degrees more than 180. So that one is 1 root 3 and 2 with a negative 1 and negative root 3. So the tangent's going to be positive root 3 over 1 minus, tangent of 45 was 1, and this is root 3. So you have 1 plus root 3 over 1 minus root 3. Let's talk rationalizing. We usually say we don't need to rationalize, but here, if it actually makes the problem substantially easier, you need to consider it. And here it does. If I multiply by 1 plus root 3, 1 plus root 3, and FOIL the numerator, I'm going to get 1 plus 2 root 3 plus 3. In the denominator, I'm going to get 1 minus 3, which is 4 plus 2 root 3 over negative 2. Or negative 2 minus root 3. And the reason that that's easier is because you could approximate that pretty decently. Root 3 is about 1.7, so negative 2 minus root 3 is like negative 3.7. You would know that by looking at this. You wouldn't know that by looking at the rationalized or the derationalized form. So rationalize when you can, and I'm going to put up your homework here. We are done.